Oh, that's good. Yeah.
All right, let's go ahead and get started. Just to remind you, homework 0 is due now, basically. The deadline is 5 o'clock, which means 15 minutes after I stop talking. There's a few minutes of slack actually built into the system, but that's it. It only occurred to me very late, as in this morning, oh wait, the deadline is immediately after class. That's a bit unfriendly. So for homework 1, I'm planning to move the deadline. And the question which I would like some feedback on is whether you would prefer that rather than leave this sort of gray area here with at the very end that's during class, whether you would prefer that I just put the homework deadline earlier in the day, or whether you prefer that I put the homework deadline later in the evening, which has its own set of problems, especially for people who want to have lives. Later in the day would mean something like 7 or 8. Earlier in the day would mean something like 2 or 3. So could I get a show of hands? How many people would prefer the deadline? Just have it before class, get it done. And how many would prefer to have the deadline a few hours after class is over? So I think that's a fairly clear majority for the later deadline. So those of you who want to get it done earlier, I invite you to finish it earlier. I'm sorry, that invitation would be absolutely meaningless to me. So let me just, the PDF file still says 5 o'clock, and the webpage still says 5 o'clock, but I'll update that. The other thing that's different about homework 1 is that unlike homework 0, which everybody is supposed to write up individually, for homework 1 and all later homeworks, you can write up and submit the solution in groups. Groups means at most 3 people. I've already been asked this a couple of times, and I'm asked this question every semester. I have a group of 4 people that we work really well together. Can we just work together as a group and submit a single solution? It's perfectly fine if you work together in a group of 4 or 6 or 25 people. But for purposes of writing up the solutions, break up into groups of at most 3. So if you have 4, just break up into 2 groups of 2. The 2 groups of 2 should write up the solutions differently. If you actually traded ideas among the 4, write each other's names at the bottom of your solutions to give proper credit, and then we're fine. I don't want this to be interpreted as you're only allowed to talk to 2 other people. But rather, we want a reasonably dense sample of your actual understanding of the material. The other thing that's different about this is the submission protocol. So we are still working out the kinks, but the system that we're going to adopt is exactly the same as what was used at the end of the semester in 374 last semester, which is there's one from each group. So one member of each group will upload your group's solution to problem 1. And so you upload the PDF file, but then there will be, in addition, a form that whoever submits the file fills out where you enter the other 0, 1, or 2 members of your group. Plus there's a form listing other group members. So the idea here is we want an automatic mechanism so that if Patrick and I are working together in a group and Patrick submits our common solution to problem 1 and then that problem gets graded, that when the graders enter the grades, I also get a grade without having to do a lot of manual labor to move things around. So the form, together with some apparently really awful scripts and playing with Moodle CSV files, and parsing CSV files and turning them into HTML files for Moodle to parse. It's a nightmare, but I think we've got it worked out. This will let us do that. If you submit the PDF and you do not fill out the form, the other members of your group will not get a grade because that's the mechanism by which we know who the group members are. And this needs to be done separately for each problem because we're not going to insist that the groups are the same. Okay. And this is all per problem. Groups can change from one homework to the next. Groups can change from one problem to the next. That's why we need to ask you to fill out this form every time. Okay. It said homework 1, aside from the incorrect deadline, is already up. The LaTeX source for homework 1 is already up. The figure in the LaTeX source is, there's the PDF file for this figure is already there, but this was not drawn with tech code, so there's not source as such for this. There's an OmniGraffle file, which is available if you happen to have OmniGraffle. But I don't write code to draw my pictures. I draw them by hand. The things in blue are links. Okay. So, are there any administrative questions? Thanks for your patience while we worked out the kinks in the submissions for homework 0. I think by now, I haven't heard any panic screaming. I don't know if Patrick's heard any panic screaming, but I think everything is working okay. All right. So, I want to continue with our discussion of dynamic programming. And in particular, I want to make an argument that there is a completely different way to think about dynamic programming than the way that we've developed it so far, which is useful because this other way of looking at dynamic programming lends itself to a wider class of problems than the way that we've thought about it before. And so, for the moment, let me sort of step back from the final destination of the dynamic programming design process. And let me stop at the state where we have a memoized recursive algorithm. Okay, so this memoized recursive algorithm is going to have, there's some input x, and it's going to have the following basic structure. I need to do some pre-processing on x. And then I need to make some recursive calls. I derive some subproblems from x. So for example, if x is a number and I'm trying to compute Fibonacci numbers, I need to compute x minus 1 and x minus 2 to pass down to my recursive calls. If x is a string, then I need to or a pair of strings that I'm trying to compute edge distance from. Then there are several subproblems that this depends on. Remove a character from A, remove the last character from B, remove the last character from both. But in general, I'm just going to say for every subproblem y, I'm going to call memo of y. And then I need to do some post-processing of x together with the outputs of the recursive subproblems. Except I, of course, have forgotten the most important part of why we call this memoization, which is that I don't do this all the time. If the answer for x is unknown, then I'll go through all this recursive stuff, and I'm going to assume that the post-processing actually gives me the answer for x, and then in the end I'm going to return the answer. Okay? So this is the basic structure of a memoized recursive algorithm. For purposes of illustration, I'm assuming here that there's an array that can be indexed by the subproblems, but that just means write it down in whatever the appropriate data structure is. Okay, so now let me describe a slightly different algorithm, which is also familiar, I hope. So let's suppose I have a directed graph and I want to do depth first search. Now, generally speaking, you don't just do depth first search. There's some action that you want to take on the graph, some output that you want to compute on the graph, that you're using depth first search to execute. Okay. Let me, for the moment, just to keep things simple, let me assume that there are no directed cycles in the underlying graph that I'm searching. And this will simplify the code. And the complications that I would need to handle those cycles are not really relevant for the point that I'm trying to make. Okay, so how do you do depth first search in V? Well, there's some, sorry, I shouldn't call it that. Revisit V. There's, some initial computation that I might want to do at V, like print an open parenthesis or something similar. And then for each edge leaving V, for some other node W, I recursively do a depth first search at W. And then after I've visited all of my descendants, I do some, post-processing. For example, I print a close parenthesis if I'm printing out a data structure. But in order to save myself time, it's possible, even though there are no directed cycles, that there might be multiple paths from whatever my start vertex is to the same vertex V, and I don't want to repeat the work that I've already done. So I need to modify this a little bit. Yeah, actually, I don't need to move that. If V is unmarked, So I'm going to assume that when I start the depth first search, there's an extra bit attached to every node in the graph, which indicates whether I visited this node previously or not. If I have visited it, the node is marked. If I haven't visited that node, the node is unmarked. And the last thing I do after I do this visit is I mark V. Okay, and I assume the pre-visit and post-visit take care of whatever whatever output I might want to produce out of this. There might actually be a return value, and I might have to deal with it in the recursive calls and so forth. But this is the basic structure. Okay, now the thing that I want you to notice is that actually let me shrink these down so I can see them side by side. These are the same algorithm. Line by line, exactly the same algorithm. Okay. When you are using a memoized recursive algorithm, well, instead of looking at whether a particular vertex in some graph is marked or not, instead I'm looking to see whether I've written down some information about some particular subproblem. I do some pre-computation on that subproblem or that node. I recursively visit a bunch of related subproblems or nodes. Related here means connected by an edge. Related here means depends in the recurrence. I do some post-processing, and then I write down the information that I look for at the very top. And in this case, that's the mark. And then, well, here I have a return thing because generally that's what memo does, but depth first search is a bit more general. But the structure of this algorithm is the same, right? And so the thing to realize here is this is just a depth first search of the recursion DAG. Okay, so what's a recursion DAG? So if I didn't have this memoization in the algorithm on the left, I would get a pattern of recursion that resembles a tree. Remember, I drew this complicated tree for the Fibonacci recurrence. And so when I want to talk about the recursion DAG for the Fibonacci numbers, what I mean is that all of the F3s are actually the same thing. It's the same subproblem. So think of those as all the same node, right? So the Fibonacci recursion DAG looks like this. I want to compute f sub n. Well, I'm going to have an edge going to f sub n minus 1 and another edge going to f sub n minus 2. And f sub n minus 1 will have an edge going to f sub n minus 2 and f sub n minus 3. And f sub n minus 2 will have edges going here. And so on, until eventually I get to the subcases, the base cases, where f2 points to f0 and f1. f3 is also going to point to f1. And this is a directed acyclic graph. There are multiple paths from the starting point of my recurrence to later subproblems. I have things that branch and return to each other, which, if I ignored the arrows, would look like cycles, but there are no directed cycles. I can't follow a cycle all the way around. And at some level, of course, I can't follow a cycle all the way around, because if I did have a cycle in this graph, the recursive algorithm would never halt. I mean, this is the reason why I don't bother with the bookkeeping when I'm thinking about this as depth first search. If there's a cycle in the recursion DAG, it's not really a recurrence. Remember, recursion is always kind of like induction. Something has to get smaller. There has to be some measure of progress every time you make a recursive call. In this case, the progress is the subscript here of which Fibonacci number you want. But really all progress means is you never get stuck in a cycle. You don't infinite loop. Okay? For edit distance, I'm not going to write the recurrence again, but the subproblems, remember, for edit distance corresponded to a prefix of one string and a prefix of another. So I have two strings of length n. That means I'll have roughly n squared different subproblems, which means I'm going to have roughly n squared different nodes. And when I'm trying to figure out what the edit distance is for a particular pair of prefixes, I need to consider the possibility that the last operation I do is a deletion, the last operation I do is an insertion, or the last operation I do is a replacement. So again, for every node, I have these three outgoing arrows, except at the very end, where you can either think of these as base cases and then they're just sinks, they don't have any outgoing edges at all, or you say, well, the only way to get from the empty string to a non-empty string is to do, the last thing I do must be an insertion. So maybe I have one outgoing edge. And then eventually these all lead down to one particular node, which represents how to get from the empty string back to the empty string. Now, in the figure that I drew last week that showed the memoization table, the subproblems are actually lined up in the other direction. The pattern of recursion is I make the initial recursive call down here in the lower right corner, which represents the entire pair of strings. Actually, I think the best thing to do is just to pull up the picture. Right, so down here, this square represents the goal. This is the initial recursive call. That means I want the edit distance between the entire string A and the entire string B. And when I make recursive calls, the recursive calls push me up and to the left. This is backwards from the order in which the dynamic programming algorithm actually evaluates the values. The values propagate, so recursion goes this way, and the dynamic programming evaluation goes that way. Okay? So when I was drawing these arrows in this figure, these are not the arrows in the recursion DAG. These are the reverses of the arrows in the recursion DAG. This is sort of how information flows from simpler problems to more complicated problems. Whereas, when I've defined the recursion DAG here, I've oriented the arrows from more complicated problems to the recursive subproblems they depend on. And again, the same is true for the Fibonacci DAG. Right? The way that the recursion goes is I start by saying, what's the nth Fibonacci number? And the Fibonacci subroutine says, I don't know. What's the n minus 1th Fibonacci number? And the recursion fairy says, I don't know. What's the n minus 2th Fibonacci number? But the way that the data actually fills in the memoization table is the other way. You start by writing down F0 and F1 and F2 and so forth. Okay. And this is a general pattern that information flows backward through the graph. Okay? So, all dynamic programming algorithms are depth first search. Okay? And in particular, all dynamic programming algorithms are depth first search in a DAG, again, because in a directed acyclic graph, because if I don't have a directed acyclic graph, I don't really have a proper recurrence to evaluate. So if I think for a moment, suppose I'm just given a DAG, right? And I want to do something that kind of smells like dynamic programming. When we were talking about dynamic programming, there was this question of what order do things get evaluated in? What subproblem gets filled in first? What subproblem gets filled in second? And so forth. That ordering has a name. If you just have a DAG. Does anybody remember what it is? Yeah. Right. It's a topological order for the DAG, and it's usually computed by topological sort. Okay? So let me show you how to do topological sort. So I'm gonna copy. This is assuming, again, I'm gonna describe topological sort, assuming that the underlying graph is a DAG. Okay, so here is my depth first search. The way that I'm going to do this is I'm going to write label, so v equals, or sorry, not equals, gets num, which I'm now going to decrement, and in the pre-processing, I'm going to say that num, the label that I'm going to, sorry, gets the number of vertices. That's topological sort. The first vertex that you post-process is the last vertex in the traditional notion of topological order. Right? So normally, the way that you would do a topological sort, for example, in the Fibonacci DAG, you would want a linear order that's consistent with all of the arrows, which means you would want a linear order that goes from f sub n down to f sub 0. So this is the traditional definition of what topological sorting does. In this particular case, that's the only topological order. For the edit distance DAG, there are many different topological orders. Right? You're always going to start here, but where you go next is kind of ambiguous. There are multiple things that work out. I actually would prefer if topological sort were defined in the opposite direction. Right? So what I would actually like is to do the following, say, well, actually I'm going to start at 0 and I'm going to increment the label instead of decrement. So now this labels each of the vertices in the order that they would be actually post-processed by depth first search. This is the reverse of the usual topological sorting order. Okay, so now this is reverse topological sort. And the reason is that this is the dynamic programming order. It doesn't matter. I mean, I'm going to get different orders depending on how I do these recursive calls. If I've got multiple outgoing edges, I could call those calls in any order I want. Depending on which order I do, I'm going to get a different ordering, but it doesn't matter. Any ordering that can be output by this reverse topological sorting algorithm is a valid evaluation order for dynamic programming. Normally, though, this is not how we come up with the evaluation order, because the underlying recursion DAG is very highly structured. If I have something that looks like a grid with arrows going all in the same direction, then it's pretty clear how to find a topological, a linear extension of this partial order. just two nested for loops. There's the cartoon with the double arrow and the single arrows. That's all you're doing is describing a valid topological order for this DAG. Okay. So it's worth understanding that there's this isomorphism, not because I want you to think about the edit distance algorithm as a depth first search, but because I want you now to be able to do other things where the recursion DAG is not so well structured using depth first search. And the first example of that we saw on Thursday was doing independent sets in trees. In the end, what did the algorithm do? It did a depth first search of the tree, and it processed the nodes in the tree in post order. This. Okay? But you don't need to restrict your attention to trees. So let me describe a prototypical problem and develop a dynamic programming solution for it. Okay, so suppose I'm just given a directed acyclic graph. I have a particular source vertex I'm going to call S. It has some, complicated nodes and edge structure. I'm not sure exactly what it's going to look like. Okay. And within this DAG, there's some natural number of paths from S to T. It's possible that that number is 0. It's possible that number is exponentially large in the number of nodes of the graph. And what I would like to find is the path from S to T that contains the largest number of edges. Okay. So if this were not in a DAG, if I just had a regular graph, no other restrictions, either directed or undirected, this problem is NP hard. It's equivalent to the traveling salesman problem. But because I have this acyclic structure, I can actually solve it in linear time using dynamic programming. So the way I'm going to do that is by following the same rules that I followed for any other dynamic programming algorithm. I'm going to start by developing a recurrence. So let me define LP from V to W as the number of edges in the longest path from V to W. And I'll come up with some recursive algorithm for this, which I'll then call with the arguments ST. Okay. So now I can write down a recurrence. It's going to have a few cases. Let me start with the interesting case. Well, actually, let me just go ahead and dispense with the interesting base case. If V is equal to W, there is exactly one path from V to W. Here it is, V. It has no edges, and therefore it has length 0. Okay? I'm going to call, when I develop this recurrence, I'm eventually going to call it with the arguments ST, but I don't want to, I want to stay generic. Okay. So if V is not equal to W, then the longest path from V to W has to leave V for somewhere. So otherwise, I'm going to traverse one edge. Actually, let me say this very carefully. Otherwise, I want to take the longest path. Otherwise, I want to take the maximum over all edges from V to some follow-on node X of 1, the charge for that edge from V to X, plus the longest path from X to W. Okay? So if V is here and W is here, then I have two possibilities for X. One of these two nodes. And so I just loop over those two vertices. For the first one, I find the longest path to W. For the second one, I find the longest path to W. Let's say W is here. Okay? Good. Am I missing anything? Yeah.
There is no path.
What?
I mean, if...
Oh, suppose there is no path from V to W. Right? Suppose in the input, somehow it happened that, say, this is V and this is W. I claim that the algorithm is correct. But I'm relying on a subtlety in the notation. If there are no edges from V to X, what does that expression at the bottom of the screen mean? What is the only thing that makes sense to interpret the what is the maximum of the empty set? And remember, whatever your answer is, when I add one element to the set, I have to get, and then I take the maximum of that thing. Remember, the maximum of the set can be defined recursively as either something, if the set is empty, or the larger of one arbitrary element and the maximum of what's left. So if the set only has one thing, the maximum has to be the larger of that one thing and the max of the empty set. So it's the max of the empty set. Negative infinity. Good. And so what will happen in this particular case is V will, the recurrence will recurse its way down to T. I'll say there's no path from T to W, so this is minus infinity. And so anything that pointed to T will have minus infinity there. And if all paths eventually lead to T, the minus infinity will bubble back, eventually reaching V again. I could say that more formally by induction on the topological order of the nodes in the graph. But the basic idea is there is a hidden base case in this expression which makes everything work. Okay. Now, if I wanted to memoize this algorithm, this recurrence, the way that I've written it down, I run into a slight problem, which is that the subproblems are identified by pairs of nodes. But there's a simplification that I can apply to make the memoization easier, which is to notice that the second argument the function is fixed, never changes in recursive calls. I'm always going from something to W. And so rather than passing W in as another argument to the function, it's probably better to do the following. Let me erase that comma and just have one argument. And just say, the target of my path is always going to be this node T. Right? So I change the specification of the function. Now it only has one argument, but the target vertex t is fixed. And in the recursive call, I only pass in one node, and either that node is t, in which case, hooray, I found it, 0, or it isn't, in which case I tell my recursive subproblems, you're still trying to get to t as fast as you can. Okay. With this simpler recurrence, there's one subproblem for every node in the DAG. Okay? So if I were to memoize the structure, what data structure would I use to record one piece of information for every node in the DAG? I'm sorry? Right, I just add a field to the nodes to each node in the DAG. And what order should I evaluate the nodes, should I fill out the data structure? Sinks first, then working my way back to sources. So reverse topological order. How do I traverse the graph in reverse topological order? Depth for search. So if I actually do this, I realize here's just the memoized recursive algorithm. Okay. V.LLP is the length of the longest path from V to T. Except, of course, this is wrong. That should be minus infinity. Let me see if I can actually write infinity. Looks right. Okay, not positive infinity. So if I find myself at t, I return 0. Otherwise, if I haven't visited this node yet, I'll do some pre-processing. I'll recursively visit each of my descendants. Here is I have this extra parameter here, length. You can imagine the edges have weights on them, and you want the longest weighted path. In the recurrence I have up there, this length is always 1. And then I recurse on each of my outgoing neighbors, and then finally I return the value. Okay, so this is the memoized recursive algorithm. If I turn that into a dynamic programming algorithm, it looks like this. Look at the nodes in reverse topological order, and then, there's no recursive calls in here anymore. By the time I am evaluating v.llp, I've already computed w.llp for every edge v to w. That's what reverse topological order means. Okay, so that is memoized recursion. This is dynamic programming. Except these algorithms are not actually different, because the way that you implement this for loop, it's perfectly okay to write this on homeworks, it's perfectly okay to write this on exams, but keep in mind that when you want to implement it, the way that you would implement visit the nodes in reverse topological order is by doing a depth first search. The only difference between the second algorithm and the first is in the first algorithm, the depth first search is explicit. And in the second algorithm, the depth first search is implicit. Whatever. Let 1,000 flowers bloom. Either of these is a perfectly reasonable way of describing this algorithm. There's only one algorithm up here. You can think of it as memoized recursion, or you can think of it as dynamic programming, or you can think of it as just do depth first search and evaluate things in post order. No matter how you do this, the running time of the algorithm is going to be linear in the number of vertices plus the number of edges, because, well, I visit every vertex at most once, because the second time I visit the vertex, I've already computed the answer for that vertex. And for each vertex, I consider each outgoing edge once. So every edge gets considered in one of these max expressions exactly one time, and that's the only place that edges show up. Yes. So I've made 2 mistakes. This should be 0, and this should be minus infinity. Thank you. Okay? Surprisingly, 90% of dynamic programming algorithms can be recast as find the longest weighted path in the recursion DAG, where the weights are determined by the particulars of the recurrence. I don't really think it's useful necessarily to think of every dynamic programming algorithm this way. In fact, there are some dynamic programming algorithms where the DAG that you're given is in fact not the recursion DAG. The subproblems maybe involve pairs of nodes or more complicated things. But it's useful to keep this in mind. And then probably in homework 2, there'll be a problem where you're given a graph and you need to do something. And if you think of that thing that you're doing as dynamic programming, you're right. And if you think of that thing that you're doing as depth first search, you're right. However you want to think of it. Okay? Any questions about this isomorphism? Okay. So the second thing I want to do today is describe a different dynamic programming problem for graphs, but again, just to maintain some fluidity, the particular problem that we're looking at, the recursion DAG is not going to be the input graph. You're going to be given a graph, and now we have to do something dynamic programming with it, and it's not going to naturally fall into this, oh, it's just depth for search. There's a more interesting structure that we'll exploit. Okay, so here the problem is exactly the reverse of what we did previously. Okay, I'm given an arbitrary directed graph. If you like, you can imagine the edges have weights. To keep things simple, let's imagine all the weights are positive. I don't want to think about negative cycles and stuff like that. Yeah. And I want to compute the shortest path from some node S to some node T. Now, if the graph is a DAG, we're already done. I just changed some minus infinities to infinities and some maxes to mins. Okay. But it is a graph with cycles in it. But because I've assumed that all the edge weights are positive, I know that the shortest path is not actually going to go around those cycles. I have some way of breaking the cycles. So we already know that there's an algorithm due to Dijkstra which can solve this problem in roughly linear time. Under these circumstances, but let me step back and think of this as a dynamic programming algorithm. Okay, or rather, maybe I should say as a dynamic programming problem. And I think in the interest of, I need to move this to the slide. Okay. So what I want to define recursively now is distance. Again, I'm going to be generic. This is the shortest path distance from V to W in whatever my input graph is. And let me see if I can develop a recurrence for it. Okay, so again, I have the base case. If V and W are the same nodes, then the best thing I can do is not move. Okay. Otherwise, I'm going to take now the min over all edges from V to X of, let's go ahead and consider the lengths of these edges. Oh, come on. V to X plus the distance from X to W. Okay? To simplify things, let me now not think about what happens when this is empty. If there are missing edges in the graph, I'll insert them and give them length infinity. Okay, so I'm going to change the problem, the way I deal with the base cases a little bit differently. So, as you might expect, there's a, writing something down for the first time, there's a problem here. Say I want to go from S to T. So I want to go from S to T, so S is not equal to T, so I need to recurse on all the children of S. Great. V is not equal to T, so I need to recurse on all the children of T. Okay, great. W is not equal to T, so I need to recurse on all the children of W. Let me do this one first. X is not equal to T, so I need to recurse on all the children of X. Okay. V is not equal to T, so I need to recurse on all the children of V. Okay. W is not equal to T, so I need to recurse on all the children of W. Let me do this one first. You see where this is going. It loops forever because the input graph isn't a DAG. So I need a mechanism to break ties. Right? I need some resource that I'm eating up whenever I recurse. And the way that I'm going to do that is I'm going to artificially add a resource to the problem. Okay, so let me move this. Try that again. Move this down a little bit. Using at most I edges. Okay, so I'm going to just add another parameter to the recurrence, comma I, and say I'm interested in only, when I make this recursive call, say st5, I'm interested in paths from S to T that use at most 5 edges. Now, the reason why I can meaningfully put this additional constraint is that I know that whatever the actual shortest path is, I know it only visits each vertex once. So when I make the initial call to this function, I can plug in S, T, and the number of vertices. In fact, the number of vertices minus 1. Okay? And now, when I make my recurrence, I need to add one more case. If I've chewed my way down, oh, actually, I should also change the recursive call. Here, let me just rewrite it. The distance from X to W that uses at most I minus 1 edges. Okay. So the original base case is still there. If I'm at V and I want to get to V using at most 17 edges, 0 is at most 17, so great, I just stand still, and that's the best thing I can hope for. If my counter has gone all the way down to 0, and I'm not at the destination, I can't get there in 0 more steps. So the only thing I can reasonably return is infinity. And otherwise, if I'm at V, it's not the destination I'm trying to get to. I pick one of my outgoing edges, and I don't know which one, so I try them all. I add the length of that edge to the path that I'm growing, and then the rest of the path has to have at most I minus 1 edges. So I've got a budget of I edges starting at V, so after taking one step, I've got I minus 1 edges left that I can spend. Okay? And now this breaks the ties. If I now want to compute the shortest path from S to T, I would call this function with S, T, and 4, because I only need the number of vertices minus 1 as my parameter. then I would recursively call like this. I'm not t, 4, 3, 2, 1, 0. Okay, I've gone too far back up. Okay, so I won't get stuck in that. Good.
So does it make the runtime there to be something like a edge square root? If you do things like that.
Well, let's think about this. What's the? We'll get to the runtime in a second, but I think there's another question here.
Do you start the recursion with E as I?
No, I start the recursion with what's the maximum length the shortest path can have, and the maximum number of edges that the shortest path can have.
But how do you determine?
The shortest path visits every vertex at most once. So the shortest path has at most v vertices, and therefore it has at most v minus 1 edges. Yeah.
Why don't you just mark that the node you visit as a pre-processing, like there?
Because I can't memorize that. This algorithm would run, and as naively as a recursive algorithm, would run in exponential time. But if the subproblem is not just this data, but rather this data together with a record of all the other vertices I visited, then there are too many possibilities for that specification for me to memorize anything.
Can you just add another field to every node, like visited?
Yes, and it would run in exponential time.
Oh,
Because if I can't memorize it, then if I have a graph that splits, and splits, and splits, and splits, I'm going to traverse all exponentially many paths from S to T by doing this recursion, and never realize that I've already computed most of the answers halfway through. Right? I'm developing this as a dynamic programming algorithm because I want to avoid doing redundant work. But in order to do that, I need to be able to specify a subproblem with a small amount of information.
there means you already computed this.
Yes, but I have to pass that information to my recursive call. And therefore, I have to include that in my memoization structure. You're right, it will work, but you can't memorize it, and the resulting algorithm would run in exponential time. Okay, because I can't memorize it. And I'm specifically, even if I nail down the order in which I traverse these edges, even if I insist that in fact the graph is a DAG, if I do what you're saying, I can actually describe a graph that would force the algorithm to run in exponential time. It's not just, I don't know how to bound it, but it really will run in exponential time. Okay, so let me change the notation very slightly. Again, applying the principle that, remember when I developed the edit distance algorithm, I started by saying, oh, what's the first thing that I want to do? And then I recurse my way down to the end of the string. Remember, when we do dynamic programming, the information flows backwards along the string. And so when I turned it into a memorized, I reversed the order in which I considered the subproblems. I chewed up from the end instead of chewing down from the beginning. So let me define this function, which is essentially the same as what I've written above. So dist I sub v is the shortest path distance from S to V. So I have a choice of what to do at the last step. And for no particular reason, because I pulled these out of two different sets of notes, here I'm calling this a weight instead of a length, but it's the same idea. Okay, and I'm writing the I as a subscript. I don't know why. I normally hate subscripts. Well, anyway, I wrote it as a subscript. Just remember, subscripts are just other arguments. Okay. Okay, so this is the recurrence I had before. I did screw something up. on the previous slide. There's actually two possibilities for the shortest path that has at most I edges. One is that this path has exactly I edges, and one is that it has less than I edges. That's what less than or equal means. If it has less than I, then it has at most I minus 1. So let me just make that recursive call. If it has exactly I, then I have some possibilities for my last step, and then recursively, the rest of the path has at most I minus 1. Sorry about missed that one detail. It'll actually turn out to be important. And notice because S would never change in this function, S is a fixed source. I'm not actually bothering to put S into the recurrence itself, although it does show up in the base cases. Okay? Great. Everybody sort of comfortable with the recurrence? This parameter I, it's something I imposed to give the problem more structure to allow me to develop a recurrence. All right, yes?
Does the algorithm still work if you drop the I minus 1 to B? Because then you'll hit. Oh wait, you put in if I equals 0.
Yes.
If you remove the if I equals 0, then you can get a 0 when I is positive.
Yes. So I don't actually need this condition.
I'm saying then you can drop the top recursive call.
No. Oh, yeah, that's true. I could simplify things by dropping the top recursive call and dropping the I equals 0, but there's a reason why I actually want to keep these. So let's run with it this way. There's multiple recurrences that actually work, but this particular one actually is the one I want. Okay, so how would I memorize this? What sort of data structure do I need? So the subproblem is specified by a vertex v and an integer I. A 2D array. Where, let me say, the rows are indexed by I, and the columns are indexed by v. Now, why does that actually make sense? We talked about this a little bit last week. I'm imagining when I say this, I'm making an assumption about how the graph is represented. So in order to reasonably talk about the vertices are, indices into this array, I have to imagine that the graph is given to me explicitly. Either in a form that automatically associates a small index with each vertex. So for example, if I have an adjacency list, every vertex is an index into that original array of linked lists. Or it's in some other form where in pre-processing I can number the vertices by, for example, doing a depth first search. But I need some mechanism to associate vertices with integers so that I can memoize into this 2D array. If the graph is implicit and I sort of create it functionally, and when I visit a node I forget about it because it's only done implicitly, then this idea won't work. Right? But that's not generally the kind of graph that you want to compute shortest paths in. Okay. And now if I want to compute a particular value of distance sub I of v, what other values in this array does that particular value depend on? What do I have to compute before I compute this? The ones above it. Not all of the ones above it. Only the ones above it that involve an edge going into V. So there's, some subset of these nodes. But, okay, fine. Let's just be conservative and say, just to be safe, I need to compute everything in the previous row before I go to the next row. So the right way to evaluate this array is the outer loop should go down. What order do I need the inner loop to go in? Whatever. So you'll notice there's no single arrow. It's because it doesn't matter. Right? Or if you want to be clear that it doesn't matter, maybe you draw a double arrow. Whatever, it doesn't matter. Okay. And now, if I actually write this down as a dynamic programming algorithm, it looks like this. Okay. So I start with the base cases where at I equals 0, and the two possibilities are I'm already at S or I'm not. And so if I'm at S, I write in 0, and if I'm not, I write it in infinity. And then for all other possible values of I, which is, again, only up to v minus 1, I look at every vertex, and now there are two possibilities. Either the distance using at most I edges is the distance using at most I minus 1, or I have to look at the outgoing edges and do some comparisons. Okay, so this part of the algorithm here, actually I should just say that. This part of the algorithm here, this is the body of the recurrence. Okay. And all I'm doing with this comparison is doing a max with the value I already, or min, the value I already have, and the value I would get by following this edge from U to V last. Okay? So, as written, this algorithm appears to run in order v squared e time. Because it looks like I have a for loop over all vertices, and then a for loop over all vertices, and then a for loop of over all edges. Is that right? No. I'm being over conservative. So what is the actual running time of this algorithm? Yeah.
Specific question first.
Yeah.
How would you represent that top ink line
This?
in your picture without writing out the explicit? How would you say that you
Here. So what I'm doing is I'm saying, I'm going to write down the value there. It's the minimum of a bunch of possibilities. I'm going to guess that it's this one, and then I'm going to do comparisons with all the others. If I find something smaller, I'll change my mind. Okay. In the actual picture, it's that. Right. In fact, it's just v times e. So this is a loop over every vertex and then over every edge entering that vertex. So inside this pair of nested loops, I'm considering every edge in the graph exactly once. And then I have an outer loop that does the multiplication by v. Okay. This algorithm has a name. As usual, it is not the name of the person who discovered the algorithm. This is Bellman-Ford. Okay, this is the Bellman-Ford shortest path algorithm. I don't know if you've actually seen this before. It's not normally presented in this particular form. It's presented in a somewhat simpler form, which I can derive for you now, so that I can, you can see exactly, what the way Bellman form is normally structured. So one thing that I want to argue is that, I said this already, these two inner for loops consider every edge exactly once. So why not separate out the initialization for the entries in the row, and then just do a for loop over every edge. Okay? Is separate, instead of nesting those, I'm doing them separately. And now this edge from U to V, this V is not the same, it's not in the scope of this for loop V. This is just separately over every edge. This is just cleaning up the code so it's a little bit more obvious what the running time is. But then there's a second optimization that I can do, which is now that I've copied the distance at level I minus 1 into the array at level I, over here when I'm doing this comparison at level I minus 1, well, the value is already at level I, so I might as well change the indices there to i's. Okay, so all I've done is taken these last 3 lines and unindented them one level and removed some minus 1s. But the algorithm's still going to do the same thing. Now it's possible that by doing the latter optimization, things will evolve a little bit more quickly to the right answer than in the original algorithm, but that only is going to help us. This is not going to change the correctness of the algorithm. And now the observation is further that, in fact, I don't really need to keep the eyes around. And so hopefully yes, I did. Okay, so instead of keeping the eyes around, I'll say, well, this first for loop here is kind of silly. The only thing I'm doing here is I'm copying the contents of row I in the table to from row I minus 1. Right. So this part of the algorithm is kind of weird. I'm just taking a row of the matrix, a row of the table, copying it down one level, and then doing a bunch of stuff in that row. Then copying it down a level and doing a bunch of stuff in that row. And then copying it down a level and doing a bunch of stuff in that row. So why bother copying? Just use one row. Yes?
Doesn't this only work if you have an adjacency matrix?
No.
Because you're assuming constant time access to the infinite edges on V.
Yes, which I get from an adjacency list. An adjacency list is by definition an array of linked lists, where each linked list is a list of all of my outgoing edges.
But that's from...
Yes, so if I want all of the edges, I say, for all vertices, traverse the list. If I want all the vertices edges leaving V, I say, for list V, traverse the list. For the entry at V, traverse the list.
It's not constant time.
Which part is a constant time? Indexing into an array is constant time. Traversing a linked list is constant time per entry in the list. That's constant time per edge. Okay. So let's get rid of that. It's redundant, and then I only need to keep one level. And then I have an algorithm that looks like this. It's just I initialize the distances at s to 0 and everybody else to infinity. And then over and over again, for every edge, if the distance is too big, make it smaller. And this last step, the intuition that you should have, is every vertex has, say here's an edge of length 5, every vertex has an estimate of what it thinks its distance from S is. So this vertex thinks its distance is 3, this vertex thinks its distance is 10. And what this if statement does is it compares the distance stored at the end of the edge to the length of the edge plus the distance at the beginning. And if the distance at the end is too big, it says, oh, that is clearly wrong. Let me change it to a better estimate of the shortest path distance. This is called relaxing an edge. This is exactly the same operation that's done inside the inner loop in Dijkstra's algorithm. And so it's sometimes seen this way. Just to relax the edge, just say this edge is part of the shortest path. I need to update the distances accordingly. And so the right way to think about Dijkstra's, about Bellman-Ford's algorithm is B times relax all the edges. And now it's clearly V times E. And if I hadn't lost you in the middle of the transformations, hopefully you believe the algorithm is correct. Moreover, it's correct even if the edges are negative, which is not true of Dijkstra's algorithm. Or at least it runs in VE time, which is not, Dijkstra's algorithm can be forced to run in exponential time. Any questions? How many of you recognize the picture? Not enough of you. This is from a phenomenal webcomic called Hyperbole and a Half. Enjoy. Thank you.
On your side, you have office hours for
Oh, for tomorrow, 4 to 5.
45.
But I'll fix the website.
What was your logic for concluding that the maximum